Our universe, seemingly infinite, has an horizon and is expanding. These facts are brought out very clearly by considering a paradoxical question raised in 1826 by Heinrich Olbers. He asked, what may seem to be a very unsound question, why is the night sky dark? On a second thought, the question begins to make some sense. Even with an unaided eye, it is possible to see approximately 2,000 stars in the night sky. If these stars are similar to that of our sun in brightness, why are they not lighting up the night sky like an evening party in a ballroom? The sense is quickly lost when one thinks about the inverse square law, but is quickly regained when one also appreciates that the number of stellar sources in a spherical shell also scales up as the area of the shell. If the density of these stellar sources are constant all over, then the number within a spherical shell of radius er is proportional to the area of the shell, I.e to er squared. So although the intensity falls as r squared, the number of sources goes up by the same factor. Thus the brightness from all these shells reaches us without any diminution and just adds up to provide an infinitely bright sky if the universe is infinite in extent irrespective of whether it is daytime or night. One possibility is that some of the stars will block off the light from the stars at their back. Even in that case, the minimal nighttime intensity would equal the intensity of at least one star. The night would be as bright as the day is. Won't the IESM gas absorb some radiation? Thin as they may be, they would undoubtedly do. However, the gas would soon come to radiative equilibrium with the starlight and would begin to shine at the same black body temperature. Actually, as long as we retain the picture of an infinitely old, infinitely large universe at the back of our mind, we won't be able to rely sensibly to the question raised by Olbers Paradox. If the universe have a horizon, then stars beyond the horizon will be locally cut off and won't make the sky bright at night. The existence of horizon seems to bring back the night sky at peace again. But it turns out that merely the existence of an horizon is not sufficient for resolving the paradox. The universe would also have to expand in time, and the photons coming from large distances are redshifted so much that they bring lesser and lesser energy depending on how far they are. We would presently discuss more about the nature of the cosmological redshift. They are not quite the same as the Doppler redshift that the light from a receding source experiences, but for the time being, we can continue with that idea. We have already seen how the successful resolution of the Olbers paradox helps us to shift our idea of the cosmos as a static object. To understand the expansion of the universe, one needs some minimal assumptions to proceed further. These are the assumptions of large-scale spatial homogeneity and isotropy. If we move away from where we are now, the average density of the universe changes radically. Only after reaching 50 mpc or SE, does the mean density assume a constant value of about 2 hydrogen atoms per cubic meter. This is the scale size for large-scale homogeneity and isotropy. Cosmology, as a theory, must be considered to be applicable only at these scales at the current time. Note that the so-called peculiar motions, like the gravitational drift of our galaxy towards M32, are not part of the process of uniform expansion of the universe. By assuming that the universe is homogeneous in the large-scale, cosmology extends the Copernican principle to all space, not just the solar region encompassing the Earth. Although people with a strong anthropomorphic view can differ strongly, most of the information obtained about the universe are carried to us by M-waves. Astrophysics is remote sensing on a grand scale. For example, it is possible to demarcate between sources just by knowing whether we are viewing the emission spectra or the absorption spectra. The light from distant sources are frequently found to have a shift. Redshift measures the fractional shift in wavelengths. It can come out to be positive or negative. Though majority of the sources are found to have a redshift, some sources do have a negative shift. It is the blue shift in the spectrum received from M31 that tells us that we have a net peculiar motion towards this galaxy. Blue shifts are also observed for other sources in the local cluster. The fact that the light from galaxies is generally redshifted to longer wave lengths, rather than beta shifted to shorter wavelengths, was not known until the 20th century. In 1912, Vestoslifer at the Lowell Observatory measured the shift in wavelength of the light from M31. This galaxy, as it turns out, is one of the few that exhibits a blue shift. By 1925, Slifer had measured the shifts in the spectral lines for approximately 40 galaxies, finding that they were nearly all redshifted. The exceptions were all nearby galaxies within the local group. By 1929, enough galaxy redshifts had been measured for the cosmologist Edwin Hubble to make serious study of whether a galaxy's redshift depends on its distance from us. Although measuring a galaxy's redshift is relatively easy and can be done with high precision, measuring its distance is difficult. Hubble knew Z4 nearly 50 galaxies, but had estimated distances for only 20 of them. If the velocities of the sources are not relativistic, the redshift is simply equal to the beta. Hubble measured galactic redshifts as a function of their distances r and plotted the quantiles Cz versus r. The data fell in and around a straight line. Hubble concluded that Cz must be proportional to r. As we can see below, this translates to the form V equals h naught r. The more distant a galaxy is, faster it is moving away from us. This 1929 discovery by Hubble has been the cornerstone of cosmology ever since.